Now that I had my hypothesis, the next step was trying to figure out what kinds of data I would need to start answering it. Using models can be a really helpful tool for figuring out what kind of data you'll need and how you're actually going to end up using that data. In order to determine if the Wara was brought to the islands by humans, I first had to figure out if humans had ever actually even been in the Falklands. There haven't been any archaeological sites found in the Falklands, so in order to begin finding them, I first had to start thinking, if I were a human floating over in a canoe from South America to the Falklands, what are the types of things that I would need to think about in order to survive there? I came up with the following things. The first, of course, is that I'm going to need fresh water. So I'm going to have to find a place where there's a nearby pond or lake or stream. Second, I'm going to need to find a place where I can land my canoe. Cliffs won't do, so it's going to have to be something like a gently sloping beach. Third, I'm going to want to be located somewhere where I can have access to food. So I'll likely stay near my beach where I can fish and look for shellfish, but it would also be nice to be near a seabird colony or a penguin colony where I can get eggs and meat. Fourth, there aren't trees in the Falklands, so I'm going to want to find a place where I'm relatively sheltered from the wind. Keeping all of those factors in mind, I can highlight a lot of potential areas where humans might have decided to set up camp. I can use these maps to pinpoint locations that would have been ideal and had all of the factors that I previously mentioned in order to survive in the islands. Maps make it possible to narrow down these places I need to go, which I'll call target locations. These target locations are the places that I will travel when I visit the Falklands to look for archaeological artifacts. If I find a place that looks like it may be an old human site, I'll do what is called a shovel test pit. That's about a 1 foot by 1 foot square dug into the ground. This will allow me to look for artifacts that are buried under the surface. As you can imagine, as I'm out walking around, even though I've pinpointed some of these areas, it still might be really difficult to determine if a site actually had humans there, because I might not find any artifacts. When humans first arrive in a location, the fire frequency tends to increase enormously. And this is because humans like to use fires for cooking, for clearing land, and for hunting techniques. So fire can be a really good indicator of when humans first arrive in a location. So how can we pick up this change in fire frequency? With charcoal. So if you think about a fire, as it burns, smoke goes up into the air. The smoke is full of tiny microscopic pieces of charcoal. As it rises into the air, these tiny microscopic pieces fall out onto the ground, much the same way that snow does, and it deposits a whole layer of charcoal all along the ground. So this layer of charcoal is a record of that fire. If we imagine that this is on a much greater scale, this charcoal covers a much greater area than just the 1 foot by 1 foot square that I plan on sampling with my shovel test. So this record, this charcoal record, gives us a much greater chance of finding evidence that humans might have been there. The way that we collect this layer is by taking a peat core sample in much the same way that ice scientists take ice cores. Peat is a lot like soil. It's made up of partially decomposed plant material that builds up in layers. One of the most important things to know about coring is the Law of Superposition. What this law states is that sedimentary layers are oldest on the bottom and youngest on the top. Let me show you what this means. As plant material grows, it eventually dies and falls onto the ground and forms a layer. In the next growing season, the plant will grow up again, die, and form a layer on top of last year's layer. What happens is we get this constant buildup of layers with older layers on the bottom and younger layers on the top. So we can model what this looks like using clay, a plastic cup, and a plastic tube. Let's pretend that this clay, the blue, represents plant material from 4 years ago. The pink clay represents plant material from 3 years ago, the green from 2 years ago, and the purple is this year's plant material. So if this is plant material from 4 years ago, and it dies and it forms this nice, even layer. And let's say at this point, there are no humans and there are no fires that happen in this layer. 3 years ago, the same thing. There's no fire. We just get this nice layer of plant material that dies and forms a layer on top of the plant material from 4 years ago. Then let's say we have a year where there's a lot of growth and it falls down and dies. But this time, there is a fire. And so we get this buildup of charcoal inside of this layer. So this is all the same year. This is what happened 3 years ago. It's a big fire year. And then we have this year's layer, and we're back to a year where we don't get any fire. So now if we want to take a core of this, what we do in the field is we take a big hollow metal tube and we drive it down into the ground. We'll model that with this plastic cylinder. So we push it down into the peat layers, and when we pull it up, we've got a core representing all of the different layers of plant buildup. And what I'm left with is a cylinder of peat. And I know that in this blue layer, that's older than what we have on the top layer, and this is called relative age. And if we look and sample, we can see that in the green part of the core, where there was a fire, we can see little tiny specks of microscopic charcoal. The relative age can give us a lot of preliminary information about how old one layer is relative to another layer. We can then take a sample from each layer and send it off for radiocarbon dating in order to find out the exact age of each layer. What this is called is absolute dating. So if we have a core that is several yards long, that can give us information over thousands and thousands of years. So in our case, if I take the peat cores that we get from the Falkland Islands and examine them centimeter by centimeter, I can learn a lot about the past fire frequency in the islands. Using computer models, I can enter this data and tell when there were major fire frequency increases. And this gives us a good indicator of when humans might have arrived in the Falklands. What we need to then figure out is when the Wara arrived in the islands. In order to figure out when the Wara got to the islands, we can date fossilized Wara bones. So far, not many bones have been found, but the few that have been found were mostly found by a young boy and his brother on their farm in the Falklands. And they were walking around and they actually found the skull of a Wara. These are the first bones that were ever found. So here we have a few examples of fossilized Wara bones. This is the back of a skull, right where the spinal cord goes into the brain. And I actually found this bone in December when we were there. This is a shoulder blade from a Wara. And this is a pelvic bone. So that's right where the hip connects in. We've sent several of the Wara bones off for radiocarbon dating, and we've gotten some pretty interesting information back. For example, we sent out a tooth, and it's given us the oldest date we have so far. It dates back to 4,200 years ago. This tells us that by 4,200 years ago, the Wara had already arrived in the Falklands. If the arrival time of the Wara is similar to the arrival time of the humans, it's likely that they probably came together. In next week's video, I'll be talking about all of the important things that go into planning and carrying out an expedition. Can you come up with a list of important things that I would need to take with me to the Falklands in order to have a safe, fun, and productive expedition?